Hello, everyone, and welcome to the second topic of the SS1 physics curriculum. Now, this topic is measurements and dimensions. And if you're seeing this video for the first time, please check out the first topic as discussed, which is Introduction to Physics. You don't want to miss any of the videos on this channel. Remember, this is Oya Learn, and we make wonderful educational videos that help you get better in your academic journey. So you can make us your short plug to always getting better or getting ahead in class. So what we'll be looking at in this topic is measurements and dimension. And before we dive into it, let me quickly mention this. You see, it's not only in physics, but in sciences in general. Measurement is a very important aspect of it. Like, you cannot do sciences without measurement, and physics even takes it with more importance. See, to prove this, you see, there is no fact at all that is accepted in science. There's no law that can be established in sciences and in physics except you can quantify it, except you can measure it. That tells you that everything that we know in physics are things that we can quantify or measure. So it is very important for us to be able to understand the concept of measurements and the concept of dimensions. Now, as part of this topic, what we expect to go through are listed here. You should be able to understand the concept of measurements and units. Now, there are some things that are very important to measurements. You should be able to mention those, and the factors that determine a usable unit in physics. You should also be able to list those. Another thing that we expect to go through is fundamental quantities and units. You should be able to define them. You should be able to mention fundamental quantities. You should be able to mention their units and even the abbreviations used to denote the units of fundamental quantities. And also, in addition, you should be able to define derived quantities and units. You should be able to mention those derived quantities. You should be able to show their derivation, that is, how were they derived, and then you should be able to derive the appropriate units for those quantities. Now, beyond that, you should also be able to explain the concept of multiples and submultiples. You see, when it comes to calculations, when it comes to measurements in physics, beyond the conventional units that we have, we also have submultiples and the multiples of such units. I'm talking about things like micro, mega, tera, giga, and things like that. Should be able to show these and relate them to different units of measurements. Now, after that, you're expected to go through measurement of these quantities, that is length. How do we measure length in the physics laboratory for senior secondary students? Please take note, for this we are limiting it to just senior secondary school. There are several other measurements of length that you can take, but we're only going to focus on the ones that we do in the physics lab of your secondary school. So we say how we do take those measurements, the instruments that are used for those, how you can calculate the error that can be made with such kind of instruments. I will also look at how we measure volume in the physics lab. I will also look at how we measure mass and weight. You see, by the time we get to this point, it's very important that we are able to differentiate clearly between mass and weight. And beyond that, we should also be able to tell the instruments used to measure mass apart from the instruments used to measure weight. And then on measurements, we should also look at how we measure time in the physics lab. You see, what so many people consider as time may not be the same thing when it comes to the physics lab in your secondary school. So we explain the concept of time for secondary school students and then the instruments used to take measurement of time in the lab. And then in addition to that, we're also going to study the dimensions of physical quantities. Now, I haven't gone through fundamental quantities, which are the basic building blocks for quantities and units we have in physics. You should now look at the dimensions of these physical quantities and be able to derive the dimensions of different quantities as well from this, which will then lead us to problem solving on measurements and dimension, where we're going to solve multiple questions from the normal classroom experience to even WASE questions to even JAMB question, because we are focusing on senior secondary students. We'll also look at some other questions on dimensions and measurements that cut across different type of exams for those who are international viewers watching the channel. So trust me, you want to pay attention to this. You want to follow from start to finish. So one thing you want to do is ensure that you are subscribed to the channel, because when you do that, and then you click this notification bell icon, every time we put out a new content on this, you will be notified and you'll be able to watch the videos. So please subscribe, and also please help us by sharing the video, because we want to reach a large number of students that need videos like this, and we cannot achieve this without you. So please help us by sharing the videos. That way it gets to reach so many people who need helpful content like this. And as always, if you have any question at all that you would like to ask us on this topic, perhaps during your study you came across a particular question that is proving a bit difficult and you would like help with it, please put all those questions in the comment section and we promise to attend to all of your questions. Now let's dive into measurements and dimensions. I mentioned earlier that measurement is a very important aspect of physics and sciences in general. And I even said that no fact is accepted, no law is established unless it can be quantified or measured. Now let's look at what measurements are and what units of measurements are. So basically we'll define them and then we'll touch on these units of measurements. Now to define measurements, we'll say is the process of comparing a physical quantity. Now the physical quantity can be length, that is in terms of distances. It could be electric current. It could be even cases like when you are looking at other types of fundamental quantities like time and the likes. So when you compare these physical quantities with a standard unit, so that you can understand it, that is what we are doing there is basically measurement. So to put it together, I will say measurement is the process of comparing a physical quantity with a standard unit to find how much of the quantity is present. Like for example, if you understand a particular unit of measurement and then you say you have 10 of that unit, it's easy to understand how much of that particular quantity you have, or that particular physical quantity rather, that you have. So now when we look at what units are like standard quantities used to express measurements. You know, we express measurements now as comparing it with units. So those units are the standard quantities that we use to express measurements. Basically, they are like the standard that we use to compare measurements, standard of measurements. Like for example, if someone tells you I had 10 plates of rice, it's easy to quantify that 10 plates there. The plates you have there is the unit. Now please pay attention. You see, for a measurement to be better understood, there are two things that is required of you as a physicist. Number one, you need a number. Okay? And then the second thing you need is the unit. Okay? Just like what I explained now, 10 plates of rice. 10 here is the quantity, the number. It helps you understand how many of it you have, and then you can then quantify that even better with the unit, which is plates. When you understand the size of the plates, then it's possible for you to fully understand the amount of food that the person ate. Okay? And when it comes to units, there are some basic parameters that define this unit. But before I get there, it's important to also note that there are different types of units. Now, the one that we use majorly in physics is often called the SI unit. Okay, now what this means, the S here stands for systemi, the I here stands for international, and then the U unit, of course. Okay, now this is French word which means international system of units. Okay, now these are the generally accepted units that are used to describe the 7 fundamental quantities that we have. So it is by these that we are able to describe all the measurements that we have. Now, let me mention that some countries choose to use their own type of units. Like for example, there's a type of measuring system or unit system known as the imperial system, now which is usually used in the United States and some parts of the United Kingdom. right? We also have the CGS system amongst others, okay? But the generally accepted one that we use to measure the 7 fundamental quantities are what we know as the international systems of units. Now, what this system explains to us is that if you are measuring length, for length we measure it in meters. If you are measuring current is going to be measured in amperes. If you are measuring temperature, this will be measured in Kelvin. Okay. Other fundamental quantities like light intensity also come into play, which is in candela. We have other fundamental quantities like time, which is measured in seconds. We also have mass, measured in kilograms. This is 1, 2, 3, 4, 5, 6. So just one more. That is number of moles, which is measured in mole. So these are the international system of units. So anytime you are measuring anything in length, you measure it in meters. If it is current, it's ampere. For temperature, it's Kelvin. For light intensity, it's candela. For time, is second. For mass, is kilogram. And for mole, number of moles, we use mole. Now, when you use other system of measurements, like say the imperial system, for example, when it comes to length, they measure in inches, they measure in miles, which is different from meters used in the SI unit. When it comes to temperature, they use Fahrenheit in the United States compared to Kelvin, which is used. Other countries choose to use the Celsius scale. So it varies. Every country can decide on which one they want to use. But the generally accepted one is the SI unit. So even in countries that are using the imperial system, when they are doing calculations in physics, they still refer to this fundamental unit of measurement. So this is why it's important that we understand this unit of measurement. And the beauty of this is that it has 4 properties that makes it understandable. Number one is that it is easily defined. Whenever you see meters, you can gauge the length of a meter using a meter rule, and then the number of that will tell you how many meters you have to arrange to get the quantity that you are defining. So it's easily defined. Another thing is that it is easily reproducible. That is, this measurement, you get the same type of measurements when no matter where you take the experiment, you still get these same measurements. Now, number 3 is that they do not vary with time or space. Whether you measure it on Earth, on Neptune, on the moon, all of these fundamental units remain the same at all these points. It's easy to define them. They don't vary by time, they don't vary by space. And then finally, you can easily multiply them and even divide them to produce what is known as derived units. So you see now, measurement is so important, and you cannot do this measurement without understanding units. So this is why the next thing we're going to be looking at now is fundamental quantities and their units. We'll show you those fundamental quantities again, show you their units and their abbreviations, and then we go on to look at derived quantities. One of the common questions that is often asked of students as regards measurement is to define fundamental quantities and fundamental units. So let's attempt to define fundamental quantities and then fundamental units, and then we go on to list the 7 basic quantities or the 7 fundamental quantities. Then we give their units and the abbreviations used for them during measurements. So let's start by defining fundamental quantities. You see, fundamental quantities are the basic quantities that are independent of others. Now, what this means is that they cannot be defined in terms of other quantities, neither can they be derived from other quantities. They are so independent. Okay? Instead, other quantities depend on them. Other quantities in this sense is the derived quantities. They depend on fundamental quantities. And just the same way we define this is how we also define the fundamental units. That is, they are the basic units that other units depend upon, because they are independent. So let's put this in writing so that we'll always remember. So we said fundamental quantities are those who are independent of other quantities. So they cannot be defined. They cannot be defined in terms of other quantities Now we can also go on to say that other quantities depend on them. So other quantities derived in this sense are gotten from fundamental quantities. Now, and then when it comes to fundamental units, so we say they are the units, the basic units other units depend on or are derived from. So this is how we will define fundamental quantities and fundamental units. Now, there are 7 basic fundamental quantities. You have to know them, their units, and the abbreviations used to describe them during measurements. So let's create a table. You can go on to create your table too. Now, on one of the columns, we're going to have fundamental quantity, then we'll have unit, and then abbreviation. Now, the basic one we have are units of length, which is measured in meter, and the abbreviation used is small letter m. Okay. Number 2, we have mass. Mass is another fundamental quantity, and the unit of measuring mass is in kilograms. Kilogram, and the symbol is kg. Okay. For number 3, we have time. Now, time is a fundamental quantity that is measured in seconds. Okay, and the symbol for this, or abbreviation for this, is small letter s. For number 4, we're going to have temperature. Now, temperature is a fundamental quantity that is measured in Kelvin. Now, note this, that you can also measure temperature in degrees Celsius, in Fahrenheit, but the SI unit is what we are writing here. So meaning you have to convert it back to Kelvin if you are working in the proper SI unit. And the symbol for Kelvin is K. Number 5, we have number of moles. Now, number of moles is measured in mole, and the symbol is MOL. Okay? We also have, for number 6, we have electric current. Now, electric current is measured in amperes, that is, the unit is ampere, and the symbol here is capital letter A. And then finally, we have light intensity, which is measured in candela, and the symbol for candela is CD. So these are the 7 fundamental quantities. It's upon these quantities and these units that other quantities depend on. You have to derive them from this. So we'll be looking at derived quantities now, and then we'll look at how we derive them from these fundamental quantities. Let us now look at the definition for derived quantities as well as derived units. So starting with derived quantities. So derived quantities, we say these are produced, okay, by the combinations of 2 or more fundamental quantities. So in other words, what we are saying is that derived quantities only come into existence based on their dependence on fundamental quantities. That is, they totally depend on fundamental quantities. Now, I recall the student once asking that is it possible to produce derived quantities by a combination of more derived quantities? Now, to answer that, the other derived quantities that are combining were initially also gotten from combination of fundamental quantities. So this definition is enough to describe what derived quantities are. It's just a combination of 2 or more fundamental quantities. There are cases where you have 4 fundamental quantities coming together, you have 3, you have as many as possible depending on what you are trying to measure or describe. So whenever what you are doing in measurement requires the combination of fundamental quantities, then you know that the quantity you are measuring is a derived quantity. Now, we can also use this concept to define derived units. So derived units, we then say these are produced, okay, by the combinations of 2 or more fundamental units. So the difference in their definition is that here you are combining fundamental quantities and here you are combining fundamental units. So if you recall when we did fundamental quantities and their units, you see those quantities we have such as length, mass, time, light intensity, temperature and the likes. You can combine them to make new derived quantities. So, and to get their units, you now combine the units of those individual fundamental quantities. And what we mean by combination in this sense is that you are either multiplying or dividing or even doing all together, that is multiplication and division in the same work, okay? And that is how we get derived quantities and derived units. So now let's list some of these derived quantities and then I will look at their derivations, that is how did we come about them. I will show the derivations and then their specific units. So to look at these derived quantities and their derivation, let us fill up this table. Now in this table we have 10 derived quantities: area, volume, density, velocity, acceleration, force, energy or work, power, momentum and pressure. Please note that these are not all the derived quantities that we have. There are still many more, right? We are just discussing these 10. So which means at the end of this video, I expect that you should also put in the comment section some derived quantities that you know, show us their derivation as well and their units too. So starting with area, the derivation for area is the product of 2 different distances, which is length multiplied by breadth. Okay, now length is measured in meters, breadth is also measured in meters. So when you multiply these two, you produce meter squared. So that is the unit of area is meter squared. Now for volume, you have to multiply three fundamental quantities to get it, and it is the product of length times breadth times height. Okay, and all of these three are also measured in meters, so meaning when you multiply them, the units will therefore be meters cubed. Okay, that is meter times meter times meter to give you meter cubed. Now we have density. Now density is derived by mass divided by volume. Now you may wonder, volume itself is a derived quantity. Yes, but it is derived from three fundamental quantities, meaning that we have four fundamental quantities coming together to give us density. So therefore the unit will be, now the unit for mass is kilograms. Okay, so per, that is divided by, unit for volume is meter cubed. So for density, we measure it in kilograms per meter cube. You could also write it like this, using the negative index form. Okay, so these two are telling us the same thing. Now we also have velocity. Now velocity is gotten by applying distance or displacement divided by time. Okay, now distance, displacement, they are measured in meters, while time is measured in seconds. So to write it in negative index form, we write meter per second like this. Now to acceleration. Now acceleration is displacement over time all divided by time again. So basically what we are having here is velocity over time. Okay, and velocity over time, velocity itself is meter per second. So when you say meter per second divided by second, this would give you meter per second squared. Okay, this would be the unit for acceleration. Now when it comes to force, force is a product of mass and acceleration. Okay, and when you put this together, mass is in kilograms, acceleration is in meter per second squared. However, you see this combination has a name, and that name is Newton, or with the symbol N. So force is measured in newtons, but know that newtons is actually kilogram meter per second square. You see, this will come handy by the time we start discussing dimensions, because it is from things like this you'll be able to derive the dimensions of physical quantities. Now to energy and work, both of them have the same derivations and units. Both of them are gotten by force times displacement. Okay, now force itself is kilogram meter per second squared. Multiply that by displacement, which is in meter. This will give you kilogram meter square per second squared, which has a name known as joules. Okay, or the symbol J. Okay, this is how we measure energy or work. Now to power. Power is done by expressing work done divided by time taken. Okay, so when you consider this, you see that work done is kilogram meter square per second squared. Now divide this by time, which is in second. This will give you kilogram meter square per second cubed. All right, and this is what we know as joule seconds. Joule per second, I mean. joule per second, because work done is joules divided by time, second. So joule per second. And then we have momentum. Momentum is gotten by mass multiplied by velocity. Mass multiplied by velocity. Mass is in kilograms, multiplied by velocity, which is in meter per second. Okay, now when you look at this, it has a name, which is Newton second. You can derive it from Newton second, because Newton multiplied by second. Remember, what is Newton? Let's do that here. Newtons is kilogram meter per second squared. Okay, now when you multiply this by second, this takes this out, so we have kilogram meter per second. So that's why it's Newton second. So you see, derivation continues like that. And then to end this one, we'll be looking at pressure. And pressure is gotten from force divided by area. It is defined as force per unit area. Now, force itself is measured in newtons. Now, area is in meter squared. So this is basically Newton per meter squared if we put it in negative index form. Now, these are some derived quantities, their derivations, and their derived units. So please do well to also add into the comment section some derived quantities you know, and also show us their derivation and their derived units. Thank you. Now, one very important aspect of calculations with measurements in physics is what we know as the multiples and submultiples. Now, you see, when taking measurements in physics lab, there are some kind of quantities that you measure that are so minute, and the only way to express them would not be in the SI unit, but in multiples, submultiples of the SI unit. And then there are some that are so large that the best way to express them is in multiples of their SI units. So that is, when we say multiples, it means you are multiplying it by powers of 10. And then when we say submultiples, you are doing the negative index of power of 10. So these are the common multiples used and the common submultiples used. So let's explore them and see what they mean. So like, for example, if you hear the term decameter or decakelvin, what that means is that the symbol for this is actually dA. That's the symbol. You see this before the actual unit of measurement. Like decameter will now be DAM. Okay, decakelvin will be DAK. Okay, this actually means multiplied by 10 with the power of 1, of course. And then in the second case, when you see hecto, by the time you see hecto, it has the symbol H. And what this means is that you are multiplying by 10 to the power of 2. So like hectometer will mean in hundreds of meter. So 5 hectometer is basically 500 meter. And just as 5 hectokelvin is 500 Kelvin, 5 hectoamperes is 500 amperes. I believe you understand the dynamics at this point. Now we also have, now these two are rarely used though, but you see from kilo, mega, giga, and tera, they are highly in use. Now in the case of kilo, the symbol is K. Okay, what this means that you are multiplying by 1,000, which is 10 to the power of 3. So when you are working in units of meter, for example, meter times 10 raised by 3 will give you what we know as kilometer. So you just make this a prefix to the original unit of measurement. So you just write that as a prefix, and then if you are using symbols, these are the symbols. So it will be K, then meter for kilometer. K amperes, that's kilo amperes. K candela, kilo candela, and so on like that. Now for mega, the symbol is capital M. Now what this stands for is times 10 to the power of 6. Okay, that is in millions of a particular value. Now for giga, it is done with the letter G, and this means times 10 to the power of 9. While tera with the capital T is times 10 to the power of 12. Now these are multiples. For the submultiple part, it retains the same thing except that it is with negative index. So the symbol for deci is D. So decimeter would be times 10 to the power of negative 1. Okay, centimeter is small c. It can also be centi any other fundamental unit. So this is times 10 to the power of negative 2. For milli, we use small letter m, and that's times 10 to the power of negative 3. For micro, the symbol is a bit different. It looks like this. Okay, when you see this like microfarad, microkelvin, or things like that, it means times 10 to the power of negative 6. And then for nano, we use small n, which means times 10 to the power of negative 9. And then finally for pico, we have small p, which is times 10 to the power of negative 12. So now when you're doing any calculations that is on measurements in physics, and you get to numbers that are so minute, you can express such numbers in their sub multiples. And then if you are dealing with numbers that are so big, so large, you can express them also in their multiples by using the symbols provided here. Thank you very much. Let us now discuss some measurements in the physics lab. So we'll be starting with measurements of length. Now, I have mentioned that when it comes to measurements in the physics lab, we are not going to be looking at all kinds of measurements of length. We are only going to be focused on the type of things that you would most likely measure in a secondary school physics laboratory. And when it comes to the measurement of length in a secondary school physics laboratory, there are 3 instruments that are used to measure length. The first instrument is known as the meter rule. Now, this instrument is actually a long bar that is graduated in millimeters and centimeters. So let's note that down. It is graduated in centimeters and millimeters. So the entire length of a meter rule is 1 meter. So that is 100 centimeter. So highest measurement is 1 meter, that is 100 centimeter. And then the lowest. Now, we are more concerned about the lowest measurement than we are about the highest measurement. So the lowest measurement that you can take with a meter rule is 1 millimeter. Now, 1 millimeter is equivalent to 0.1 centimeters. So this is the lowest measurement you can take with a meter rule. And that means that by the time you're taking measurement, the minimum error you can make, or as a maximum error rather, is half of 1 millimeter. So basically that's 0.5 millimeter. That's the maximum error you can make. So when you are taking measurement with the meter rule, you can round up to half of a millimeter when taking your measurement. Now that's for the use of meter rule. Now the other instrument used to measure length, that's for B, is what we call the vernier caliper. Now, you see the vernier caliper is used to measure even more precise lengths, that is smaller lengths as compared to what you will measure with the meter rule. Now, it's important to note that it is also graduated in centimeters and millimeters. Okay, but in its own case, it has 2 scales. Okay, it has 2 scales, which are the main scale. The main scale is the one graduated in millimeters and centimeters, and then we have the vernier scale. The vernier scale is basically 0.9 centimeters divided into 9 different divisions, right? So what happens with this is that when you take measurements with the vernier caliper, the kind of measurement you can take with it is like, for example, if you're trying to find the thickness of a meter rule, you can do that using a vernier caliper. If you're trying to find the diameter of a ball, a small ball, you can do that using the vernier caliper. If you're trying to find the internal and external diameter of a tube, you can also do that using the vernier caliper. Now, this is because it gives you measurements to a precision of 0.1 millimeters. That is lowest possible measurement. Is 0.1 millimeter, which is equivalent to 0.01 centimeters. Okay, so you see that it allows you to measure even more minute length as compared to the meter rule. Now, in case if what you want to measure is now very tiny as compared to the rest of this, the next instrument we use in that case is known as the micrometer screw gauge. Micrometer screw gauge. Okay, now this one is used to measure very tiny lengths. I'm talking about lengths in the order of like the diameter of a wire or even the thickness of a paper. You see how tiny that can be. Those are the kind of measurements you can do with a micrometer screw gauge. So it has more precision as compared to the meter rule and the vernier caliper. Now it is graduated in millimeters, and then it has main scale and vernier scale as well. Okay, so now when it comes to the lowest measurement you can take with the micrometer screw gauge, lowest measurement, for the lowest measurement, what you can measure is 0.01 millimeter, which is equivalent to 0.001 centimeter. So you see, it gives you room to even measure more minute length as compared to the other two. Now, these are the three instruments used in the physics lab to measure length. If you want to see how this is used, you can check out our videos on practicals where we show you how to use these various instruments. And don't forget to give us a like and also ensure that you are subscribed to the channel, and also ensure that you share the videos so that I can reach many more that needs helpful content like this. Thank you. Having explored how you can measure length in the physics lab, now let us look at how we do the measurement of volumes. Now, I would first say that to measure the volume of an object, it depends on the shape of that object. So we'll be looking at different types of objects and their shapes that they have, and then we'll look at how you can get the volume of such type of object. So we'll be starting with a regular block, a rectangular block. Now, if you're asked to find the volume of a rectangular block in a physics lab, now there are some things you need to measure first. So you measure the length, you measure the breadth, and then you measure the height. Now you do this using appropriate instruments. Now don't forget that when it comes to measuring length in the physics lab, the instrument we use is the meter rule. However, if the rectangular block you're trying to measure has very small height, you can use a vernier caliper to find the height while you use the meter rule to get the length and the breadth. Now, when you have these values measured, what you now do is you apply volume equals length times breadth times height. So by doing this simple calculation, you can then get the volume of the rectangular block. Now, if what you want to measure the volume of, that is in case of number 2, is an irregular solid, that is a solid that does not have a particular shape or the type of shape that we conventionally work with when solving for volume, there is a simple experiment you can do to get the volume of such a shape. So what you're going to do is you're going to get a measuring cylinder that particular solid can fit into. So what you're going to do is, into a measuring cylinder, you're going to fill it with a liquid that solid will not dissolve in. So for example, if you're trying to find the volume of a stone, you can use water, right? But if you're using something that can dissolve in water, you have to look for another liquid that it will not dissolve in. So when you put it, let's assume this is the measuring cylinder, right? And then it is filled up to this point. Now you're going to lower in the irregular solid. Let me draw a shape that is quite irregular here. So you're going to lower it into it such that by the time it gets totally immersed in the liquid, okay, when it gets totally immersed in the liquid, you see that the water level in that measuring cylinder will rise. Okay, so you see this distance here. This distance here is the volume. So basically what you do is you tighten the irregular solid and you dip it into a measuring cylinder that is filled with a liquid that solid will not dissolve in. So you see that the change in volume there, the displacement, volume of liquid displaced, okay, is equals the volume of irregular solid. So that's how you find the volume of an irregular solid. Now, when it comes to finding the volume of a sphere, to measure the volume of a sphere, say like you want to find the volume of a ball bearing. It's a very small spherical object. The first thing you want to do is you want to measure the diameter. Okay, now the instrument you're going to use to measure the diameter of a ball bearing is the micrometer screw gauge. So let's note that here, using micrometer screw gauge. Okay, so once you measure this, you can then apply the equation where volume of a sphere is given as 4/3 pi r cubed. Okay, now one thing you always have to put in mind here is that r is actually diameter divided by 2. So after getting the diameter using the micrometer screw gauge, you'd have to divide that by 2. Or another way to go by it is to impute the value of the diameter divided by 2 into this equation, and you will still get the volume. Just remember to cube diameter and cube 2 as well. That will give you 4 pi d cubed over 3 multiplied by 8. And then when you resolve that, you get a simpler equation that you can use to find the volume. Now, that's for the case of a sphere. Now, number 4, if you're asked to find the volume of a thin wire, now the first thing you want to do is you measure the diameter, okay, using micrometer screw gauge. Now after that, you then measure the length. You measure the length using meter rule. So once you have these two values, you can then go on to find the volume of the thin wire. Now what you apply is that volume equals pi r square L. Okay? Now recall that this r can also be d over 2. So if we put that into the equation, we can say pi d square L over 4. So these two equations works when you're trying to find the volume of a thin wire. Now finally, you can also find the volume of liquids in the physics lab. Now to use this, you can either use a volumetric flask . Now the thing about volumetric flask is that they are already graduated in the sense that they have a measurement that they can take. So there are some volumetric flasks that are designed for just 1 liter or 1 dm cube. There are those that are designed for 3 liters. There are those designed for 5 liters. So depending on the volume you are asked to measure, like if you have to measure 3 liters of a particular liquid, it's best to use a 3 liter volumetric flask. And if you just want 1 liter, then use the 1 liter volumetric flask and you get the accurate measurement you need. However, if you have to measure between some values, there are other instruments we can use for this. Like you can use the burette. The burette can measure up to about 50 cm cube of a liquid. So up to 50 cm cube of liquid. Another instrument you can use is the measuring cylinder. The measuring cylinder also has its own graduations. There are the ones that can only take less than a liter. There are those that can take more than a liter. It all depends on the volume of liquid that you want to measure. Now, the difference between a volumetric flask and the measuring cylinder is that in the case of a measuring cylinder, there are graduations. So if you just want a certain amount of the liquid, you can use the measuring cylinder. Unlike the volumetric flask, that is only a specific volume that it does. Now, another instrument that measures specific volume like that is known as the pipette. Now, pipette can either measure 25 cm cube or 20 cm cube. Although there are smaller pipettes like the dropper pipettes and the likes, but most other pipettes that we use in the physics lab measure this particular volume. So it all boils down to, first, what type of object are you measuring the volume of? Then secondly, which instruments would you be required to use on your way to getting the volume of the substance you are asked to measure. So to recap this, for rectangular block, you have to use length times breadth times height, but first you must measure the length, the breadth, and the height using appropriate instruments, which depends on how long these different lengths are. Now, the case of the irregular solid, remember, all you have to do is immerse it into a fluid or a liquid that it will not dissolve in, and then you observe the difference in liquid, that is the amount of volume of liquid that is displaced after it is fully immersed in that liquid. That displacement tells you the volume of the irregular solid. Now, and then for the sphere, to get the volume, you're going to apply 4/3 pi r cubed. Now, don't forget that you have to get the diameter first by using a micrometer screw gauge, and then you apply radius equals diameter divided by 2 to get the radius that you use in this equation. Now, for the case of thin wires, what you have to do is measure the diameter of the wire using the micrometer screw gauge, and then you also measure the length of the wire using a meter rule. And then you put all of those values into the equation V equals pi r square L or pi d square L over 4, where this place I use diameter straight, and here you have to get your radius by dividing diameter by 2. And then finally, for the volume of liquids, there are different type of instruments that are used for this, and it depends on the volume of the liquid you wish to measure. So if you're trying to measure in liters, you can use the volumetric flask for that. If you're trying to measure in cm cubes, you can use burette, you can use measuring cylinder, and you can use pipette. But don't forget that volumetric flasks have fixed volumes that they measure, and the pipettes also have fixed volumes that they measure. However, for burette and the measuring cylinder, they are graduated from one point to another. So it all depends on the volume you are asked to measure. So please, if you have any question on this measuring technique, please put it in the comment section, and please don't forget to like and share the video. Thank you. Now, when it comes to the measurement of mass and weight in the physics lab, now we often say that we do this using balances. However, there are differences between the balances that you use for mass and that for weight. But it all starts with understanding what mass is and what weight is. So we can say mass is the amount of stuff that makes up an object. And the thing about mass is that it does not change with time or location. So it's something that remains constant. On the other hand, for weight, weight is the effect of gravitational pull on an object. Okay. So when you are finding the weight is often mass multiplied by gravitational acceleration. Now, when you want to measure mass, for mass, you can measure it using either a beam balance. Now, if they are tiny particles, you can also use chemical balance. And then you can also use the lever balance. These instruments can be used to measure the mass of an object in the physics lab. Now, when it comes to measuring the weight, we use the spring balance. The spring balance. Now, this helps you to measure the weight of an object. Now, it's important to also note that when you know the mass of an object, you can easily get the weight by just multiplying it by the effect of gravity at that location, that is, gravitational acceleration at that point. And that is what spring balance puts into account. And that is why if you observe so many spring balance, even chemical balance and the likes, they often have that something that shows you the mass on one side and weight on the other side. And there's also an instrument that can measure both of them. You just have to set it up. So when you consider the digital balance, which is the one that is mostly in use these days, for a digital balance, you can measure either mass or weight. So it doesn't matter, you just have to set it up and then measure. But one thing you have to take note is that when you are using the digital balance to measure the mass of something that is in powdery form, for example, or something that is in liquid form, you have to use a material to hold it. So you have to subtract the mass of that material from the eventual mass when you put in that material into it. Like say if you have your chemical balance or your digital balance now, and then you place a beaker on it, it will measure the weight of that beaker before you then pour in the material, whether it is in powdery form or it is in liquid form. Then you find the eventual weight, which you now find the difference of both to find the weight of the material you have put into the beaker. Although some of them also come with a special function called the tar. When you click the tar button, it will immediately subtract the mass of the material that you are using, whether it's a beaker or it's something that you just spread on the digital balance. It will take it back to zero and measure only the mass or the weight of the material in question. So this is how we measure mass and weight in the physics lab. Another thing that you could be asked to measure in the physics lab is time. Now, when it comes to time, everybody has their definition for time. But as far as physics goes, we are looking at time as that which actually distinguishes between events by using before or after. Let's put that down. Time is that which distinguish between events using before or after. Okay. Now, when it comes to the measurement of time in the physics lab, you have to recall that the SI unit for measuring time is in seconds. So we don't measure it in hours, we don't say 3 p.m., we don't say 3 a.m. in the physics lab. We measure different events using seconds. And the instruments required, the instruments for measuring time, the instrument is either a stop clock or a stop watch. Now, both of them measure time in seconds. For example, if you are conducting an experiment and you are supposed to measure the time taken for 10 or 20 oscillation of a simple harmonic motion, you use a stopwatch or you use a stop clock. Some of them are in analog form, some are in digital form. So whichever one you use, it will measure the time for you accurately. Now that we have studied how to measure different quantities in the physics lab, let us now look at the dimensions of physical quantities. Now, when we say dimensions of physical quantities, we mean the physical nature of a quantity. Now, there exist three physical nature of a quantity, or three dimensions of a quantity. Now, the first one is known as the dimension of mass. Dimension of mass. This is represented in a bracket like this with the letter M in capital letter, that is uppercase form. And then we also have the dimension of length. Dimension of length. This is represented with the letter L. Remember, all of these are in uppercase. And then the third one is the dimension of time. Dimension of time. Now, this is represented with T in a bracket like this. Now, when it comes to fundamental quantity, it can either be the dimension of mass, dimension of length, or dimension of time. As in, these are the physical nature that describe the quantities you are talking about, whether it's that of a mass, that of length, or that of time. They can be represented by any of these, depending on what you are measuring. However, when it comes to the derived quantities, you get their dimensions by the multiples of this. You can multiply, divide, and do different types of arithmetic to get the dimensions of such quantity. Now, to understand this, let's consider the dimension of velocity. Dimension of velocity. Okay? To find the dimension of velocity, remember that velocity is distance or displacement over time. Okay? Now, distance or displacement is a fundamental quantity, and the dimension of distance is what? Is in L. Okay? Now, we have to divide this by the dimension of time, and dimension of time is written like this. Now, we don't leave our answer like this. It has to be in a straight line form. So it means we have to convert this into the negative index form. So dimension of velocity will then be written as L. Then when this becomes negative index, to be t to the power of -1. And we can put both of them in a bracket like this. So you see, this is how you get the dimension of derived quantities. So now let's go on to look at different questions on this. There are so many questions that could be set. So we'll look at different types of it, and then we'll solve them so that you learn. And don't forget, if you have any question on this also, you can also drop it in the comment section. Now let's solve some problems on dimensions of physical quantity. Let's solve some problems on dimensions of physical quantity. Now this question itself says we should deduce the dimensions of force and then pressure. So let's solve for force here. The dimension for force. Force is mass multiplied by acceleration. So if you know the dimensions of these quantities, you can then put them together. Otherwise, you just take it step by step. Now, in this case, the dimension for mass is m multiplied by. Now, for acceleration, we're going to be considering velocity over time. So what this takes us to is that we have m like this. We have already solved for velocity before, and what that gave us is L to the and t to the power of -1. So all of this now will be divided by t again. So when we put all of this together, we have m L t to the power of -2, because when this goes up, it becomes -1, and then you have to add the power. So this will be the dimension of force, m L t to the power of -2. Now let's apply the same steps to find the dimensions of pressure. Now for pressure is force per unit area. Okay, so what this implies is that we have to have the dimension of force first, which we have solved here as m L t power of -2. And now we have to divide this by area, which is length times breadth. That is, we have L squared. Now, when you make this a straight line equation, you'll be having m l t minus 2 multiplied by this will now become negative index like this. So you see that when you work with this, you have to add their power. So our final answer here would be m. Now this times this will give you l to the power of negative 1, and t still carries negative 2. So there you go. Here's the dimension for force, and here is the dimension for pressure. Let's solve this WASSE question still on dimensions of physical quantities. Now this question says, at what respective values of x, y, and z would the unit of force, that is the Newton, be dimensionally equivalent to m to the power of x, l to the power of y, and t to the power of z? Now, in order to do this, we have to first get the dimension of force. Now, we have done that earlier, so let's just put it up. We know that the dimension of force, which is actually mass times acceleration, gave us the dimension m to the power of l to the power of t raised to power 2 multiplied by t to the power of negative 2. Now this is the dimension for force. So all you have to do is equate this to what we are given. So that is, we have m power of x, l power of y, t power of z equals m l t minus 2. Now from what we have here, we can just begin to compare them directly. So if m power of x equals m, what this implies is that x is 1, because this is power of 1. And if we follow this, we see l to the power of y equals l. What this implies is that y is 1. And then for z, we have t to the power of z equals t to the power of negative 2. Now this implies that z equals minus 2. So the values of x, y, and z are 1, 1, minus 2. And that's the solution to this question. Let's solve this WASSE question from 2023 on dimensions of physical quantities. Now please feel free to go through the question, pause the video, and try this yourself, and then you can compare your answer with that gotten at the end of this video. And also don't forget to leave a comment of how well you did at the end of the video. Now this question says, the force F acting on the wings of an aircraft moving through the air at velocity v and dimension and density, now this symbol is to represent density, is given by the equation F equals, then we have k v raised to power x, density raised to power y, and area raised to power z. Now where k is a dimensionless constant and a is the surface area of the wing. So we have to use dimensional analysis now to find the values of x, y, and z. So what I expect that you do first is to equate both sides, starting from this equation here that we have. We already have F equals k, v to the power of x, density to the power of y, and area to the power of z. Now what you have to do is to bring in the dimensions for each of these, okay? Now the dimension for force, that is m l t minus 2 equals, now k has been said to be a dimensionless constant, so it doesn't have dimension. So we can then move to the next one, which is v. Now v is velocity, and if you follow, when we solved for the dimensions of velocity earlier, we got that as lt minus 1. Now remember, velocity still carry power of x here, okay? Now we have to multiply this now by that of density. Now if you recall, density is supposed to be mass over volume. Now mass has dimension of m, volume has dimension of l cubed. This will give you ml minus 3, okay? So we put that here, ml minus 3. Now recall, this would give you power of y. And then for area is length times breadth, so that will be l squared. And remember, this carry power of z. So now let's simplify this. we have mlt minus 2 equals, from here we can say this is L power of x and t power of negative x multiplied by m power of y, okay, and then L power of negative 3y, okay, and then here we have multiplied by L2z. So now we can then go on to multiply L by L, M by M, T by T, like that, such that we have mlt minus 2 to equals, let's start with m. Since this is the only m we have, we write it as m raised to power y. And then we can then go to L. Now for L, what do we have? This is L. Here we have x. Here we have minus 3y. And here we have plus 2z. And then we now multiply this by t. We only have one t, so that will be t minus x. So we can start with any of them. So I would like to solve x, then y, then z. So to start with x, I'm going to equate where we have x here to what we have here. So you see that we have t minus 2 equals t minus x. Now what this implies is that minus x equals minus 2, which means x equals plus 2. So we have the value of x already. Now let's solve for y. To solve for y, we will equate m. Remember, this is power of 1 equals m power of y. What this implies is that y equals plus 1. And then for the final one, we go to L. Now here we have L power of 1 equals L power of x minus 3y plus 2z. Now what this implies is that 1 equals, what is x? X is 2 minus 3 into y. Y is 1 plus 2 into z. So we say this is 2z. So from here, we can see that we have 1 equals, now this will give you minus 3. Minus 3 plus 2, that's minus 1 plus 2z. What this implies is that 2z equals, when this goes here, you get 2. That is z equals 1. So from here now we can write out all that we have. So for x, x is 2, y is 1, and then z is 1. So we have used dimensional analysis to find the value of x, y, z. So we've gotten the solution to this question. Now please don't forget that you can always trust us to give you educational content like this. And one way you can support us to always do this is by ensuring that you are subscribed to the channel. So please take a moment of your time, click the subscribe button. You can also hit the notification bell icon so that you get alerted every time we put out a new content. And please don't forget to like and share the videos. This way we can reach many more students who need helpful videos like this. So we've come to the end of the week 2 topic, which is measurement and dimensions. We'll be going to the next topic now. I'll see you in that video. Bye for now.